Hello everyone and welcome to a new video presented to you by the MZH guys. Today we're gonna see how we can solve nonlinear systems of the form x plus y equal to s and x times y equal to p. And before going into the details, we're gonna put a quick reminder here of what we did in theory lesson number 2, where we learned how to solve second degree equations. So we start with a polynomial of degree 2, p of x is equal to ax squared plus bx plus c equal to 0. And we will assume that this is a purely second degree polynomial by assuming that a is different of 0. And we saw in TL2 video that in order to solve this, we need to calculate this parameter that we call delta, which is b squared minus 4ac. And from there, we can derive the solutions for our equation. If delta is non-negative, we can derive that the polynomial or the equation p of x equal to 0 has two solutions. x1 is equal to minus b plus square root of delta over 2a, and x2 is equal to minus b minus square root of delta over 2a. So this is kind of what part of what we did in the last video. Now we're gonna build on that, and you'll see why I did this reminder. We're gonna build on this to derive some important results that we're gonna use to solve this nonlinear system problem. So let's start first by writing this proposition here that has three parts. So and it relies on the case delta non-negative. The first proposition stipulates that x1 plus x2 is equal to minus b over a. The second one is x1 times x2 is c over a, and 3 is a direct result of these two. We can write that p of x is equal to a times x squared minus x1 plus x2 times x plus x1 x2. And in red here, I'm gonna try to give you the proof of this. You can skip or go forward in the video if you want to skip the proof, but it'll be very beneficial for you to know where these results come from. So let's start by 1. It is very straightforward. We just replace the expression of x1 and x2, and we calculate x1 plus x2. So x1 is minus b plus square root of delta over 2a, and x2 is minus b minus square root of delta over 2a. And we put these two terms under the same denominator, and then we get this minus b plus square root of delta minus b minus square root of delta over 2a. And then we can simplify by square root of delta, and then we will get minus 2b over 2a, and then we simplify by 2, and then we get the result x1 plus x2 is minus b over a. So this is pretty easy. Now the x1 times x2 will be also easy, but involves a little bit of manipulation compared to the first result. And we start from there. So x1 times x2 will be equal to minus b plus square root of delta over 2a times minus b minus square root of delta over 2a. And we know if we have a over b times c over d, it is equal to ac over bd. Numerator times numerator over denominator times denominator, and that's what we do here. And we get to this line here. And after that, what we do is we use the remarkable identity of degree 2, which is a squared minus b squared is equal to a minus b times a plus b, but we use it in the reverse order. And then we get here minus b squared minus square root of delta squared, and then we get b squared minus delta. And we leave for a square in the denominator. And from there, we're gonna replace the expression of delta in the numerator, and then we get b squared minus b squared plus 4ac over 4a squared, and we just simplify by b squared, and then we get 4ac over 4a squared here, and then we simplify by 4a, and then we get the result x1 times x2 is equal to c over a. Third result is pretty straightforward. We just write p of x as a times x squared plus b over a x plus c over a, and we just factored by a, and now we see the b over a and c over a terms appear, and because we know that x1 plus x2 is minus b over a, so then we just replace it here, and we know that c over a is x1 times x2, which is here, and then we get the result that we wanted. So we're gonna move forward, and now we'll go straight to the problem at hand. So let's consider the nonlinear system in R squared. X plus y equal to s and x times y is equal to p, where s and p are real parameters. And we know that s because it refers to sum and p refers to product, but you can name it as you wish. And also let s be the set of solutions of this nonlinear system that we called ns, referring to a nonlinear system. So to start with, we notice that this nonlinear system is a symmetrical one. What I mean by that is that the role that x plays is exactly the role that y plays, because if x plus y is equal to s, then y plus x is equal to s. And same goes for x times y equal to p, then y times x is equal to p. So x and y play a symmetrical role, and therefore if you can get a pair x naught y naught as a solution of this system, you can imply that y naught x naught is also a solution of the system. Now that we know that, we can go and prove a very important result, which says that x naught y naught is a solution of this nonlinear system is equivalent to say that x naught and y naught are roots of the polynomial x squared minus sx plus p. Let's assume that x naught y naught is a solution, and let's prove that x naught and y naught are roots of the polynomial x squared minus sx plus p. And before we start doing that, for the proof for both ways, we're gonna name the polynomial x squared minus sx plus p as p of x. And let's start. So let's assume that x naught y naught is a solution. So if they are a solution, then we know that x naught plus y naught will be equal to s, and x naught times y naught is equal to p. Now let's test and see if x naught is root of p. So we evaluate the polynomial p in the point x naught, and then we replace x by x naught. So we'll get x naught squared minus s x naught, but s, we know now that it is x naught plus y naught from this assumption that we did here. And then plus p, but p is equal to x naught y naught from the assumption above. From there, we just expand the expression, and we find that p of x naught is equal to this. And when we simplify everything, we get that p of x naught is equal to 0. And you can do the same for p of y naught using the same techniques, and then you'll arrive that p of y naught is equal to 0, and therefore x naught and y naught are roots of p. So we did it in this way. Now let's go the other way. Now let's start with, let's assume that x naught and y naught are roots of p. And this is where the preliminary result that we derived will be handy. Because x0 and y0 are roots of p, then we know that their sum will be equal to minus b over a. But minus b in this case is minus s, and a is equal to 1. Because if you recall, our polynomial p is x squared minus sx plus p. So in this case, a is equal to 1, b is equal to minus s, and c is equal to p. And then therefore, minus b over a would be equal to s, and the product of these roots will be equal to c over a, and c over a is p over 1, which is p. Therefore, we proved that x0 and y0 are solutions of the nonlinear system because their sum is equal to s and their product is equal to p. So let's go back to this result and look at it for a second, and because this is a very important result. So what did we prove? We proved that x0 and y0 are a solution to this nonlinear system is the same as x0, y0 are roots of this polynomial x squared minus sx plus p. And therefore, you'll notice that then if we just solve this polynomial, which we know how to do it, then we can get the solutions to this non-linear system. So kind of we transform the problem at hand to an equivalent problem that is easier to solve. And this is a trick that we always do in mathematics, where if you have a problem that looks difficult, we transform it into a more manageable problem that is easier to solve. All right, so let's continue from here, and now let's derive the solutions of this nonlinear system. But to start with, we're gonna have the first proposition saying that the set of solutions of this nonlinear system is not empty, is equivalent to say that the parameter p is less or equal than s squared over 4. So the system will have solutions if and only if p is less or equal than s squared over 4. Second proposition is, now if p is strictly less than s squared over 4, then the set of solution is given by two elements, two pairs, x0, y0, and y0, x0, and the expressions are given here. And if p is equal to s squared over 4, then the set of solution is given by x0, x0, which is one pair, so one element, where x0 is s over 2. All right, so the proof of the first result. So let's start and try to prove the first proposition. Okay, so the set of the solutions at hand is not empty, means that there exists. So this symbol here, you're gonna see, we're gonna have a logic lesson where you're gonna know what these symbols means. But in English, this symbol just means that there exists. So this E, flipped E, or mirrored E, is actually there exists. Okay, so now we said S is not the empty set, is equivalent to there exists a pair x0, y0 in R squared such that x0 and y0 are solutions. So we didn't do anything here. And now we're gonna replace this expression here with its equivalent part that we've shown just minutes ago. So we're gonna replace it by x0, y0 are roots of x squared minus sx plus p. And that's what we did here. All right, so and we know now that x naught and y naught are roots of x squared minus sx plus p, and we will use TL2. That is equivalent to say that delta of that polynomial is actually positive. And we know that delta is b squared minus 4ac, and in this case it'll be delta is equal to s squared minus 4p, and this becomes equivalent to p is less or equal to than s squared over 4. So we proved the first result. Now let's continue to the second result. Now let's assume that p is strictly less than s squared over 4. Then we know that the roots of this polynomial are given by minus b, which is s, plus the square root of delta that we derived here, over 2a, but a is 1, so it'll be just 2 here. And same goes for y naught, except that we have minus square root of delta. And after that, we saw a remark where we said that if you have a solution x naught, y naught, because the problem is symmetrical, then y naught, x naught is also a solution. And therefore, the set of solutions for this problem is given by the two pairs x naught, y naught, and y naught, x naught. And x naught is equal to s plus square root of s squared minus 4p over 2, and y naught is given by s minus the square root of s squared minus 4p over 2. Now what happens if p is equal to s squared over 4? Then in that case, the delta of the polynomial x squared minus sx plus p becomes 0. And in that case, we have a double solution to the polynomial given by x naught is equal to minus b over 2a. And that leads to x naught is equal to s over 2. And therefore, we can say that the set of solutions for this problem has only one element given by x naught, x naught. All right, so we know now how to solve this problem in the general case, but would like to discuss with you some special cases where just by looking at the system, you can know if the system has solutions or not. And there is a special case where if you see p is non-positive, then you can immediately deduct that this system has solutions, and they're given by x naught, y naught, y naught, x naught. And if you see that p is equal to 0, depending on the value of s, you can derive what the solutions of this system are. And you can see it here. If s is non-zero, then the set of solutions is given by the two pairs s0 and 0s. And if s is equal to 0, then the set of solutions has one element 0, 0. And the proof of this is simple. The first proposition, we just see that if p is non-positive, then p automatically becomes strictly less than s squared over 4. And therefore, we can say that the set of solutions is given by this, because we saw that case. All right, second proposition is when p is equal to 0, x times y is equal to 0, and therefore x is equal to 0 or y is equal to 0. And then we go and use x plus y is equal to s. And if x is equal to 0, then y will be equal to s. And if y is equal to 0, then x will be equal to s. And therefore, we derive the set of solutions to this problem given here, depending on the value of S. Next thing we're gonna do is we're gonna go and try to give a graph illustration of what we're talking about here. And let's start. So let's start with the main cases. The main case, which is given by P, is strictly greater than S squared over 4, will give you no solutions to the problem. And you're gonna see in our next videos how to graph such a function S squared over 4. And by the way, this graph given here is actually P as a function of S. So the graph here in blue that you see here is actually the graph of S squared over 4. And the fact that P is more than S squared over 4 is given by the dashed lines above the parabola in the blue line. So if P is situated in that area of the plane, then the nonlinear system has no solutions. If P is equal to S squared over 4, which coincides exactly with the blue parabola, then you can say that the set of solutions has one element given by x naught, x naught. And if P is strictly less than S squared over 4, and you can see the dashed lines in green in the graph, if P is in that region, then the set of solutions has two elements, x naught, y naught, and y naught, x naught. And we can also add the special cases if we want, and we discussed those. The special case P is non-positive. You can see it here in the lower half plane. And that is the plane with the equation P non-positive. And in that case, it is a subcase of this one here. And therefore we have the same set of solutions. The only difference is that without even evaluating S squared over 4, we know that the nonlinear system has solutions. And the last case is when P is equal to 0, which is given by the purple line that you see on the graph. Then depending on the value of S, you will get either two elements in the solutions given by S0 or 0S, or you'll get one element given by 0, 0 if S is equal to 0. Now let's summarize the results that we derived in this theory lesson. The idea is to solve the nonlinear system x plus y equal to s and x times y is equal to p. Now you know what you should do. First, we need to calculate s squared over 4. And then we compare s squared over 4 with p. And the first case is when p is strictly greater than s squared over 4, then there are no solutions in the set of real numbers. If there is exact equality between these two numbers, then the set of solutions of this nonlinear system has one element given by x naught, where x naught is given by s over 2. If p is less than s squared over 4, then in that case you have two elements in the set of solutions given by x naught, y naught, and y naught, x naught, and the expressions are given here. All right, so now let's see if we can use the theoretical expressions that we derived to solve some real examples. All right, so example number 1, we want to solve the nonlinear system x plus y is equal to 3 and xy is equal to 2. And you'll see that I put the s term in green and the p term in blue. So in the proof, you can see where those numbers are used. We're gonna see if we can use one of those special cases where p is non-positive. And you can see here that p is equal to 2, which is non-negative. So potentially the nonlinear system could have no solutions, but we can't know until we evaluate s squared over 4. But when we evaluate s squared over 4, we find that it is equal to 9 over 4, and this number is strictly greater than p. And from the chart that we put forward, we see that the non-linear system then has two solutions in R squared, which are given by x naught y naught and y naught x naught. And then we can write the expressions of x naught and y naught by using these two formulas here. And let's do that. So x naught will be equal to s, which is 3, plus the square root of s squared, which is 3 squared, minus 4p over 2. And this will give us 2. Same for y naught, but with a minus here, and then we'll get 1. So in that case, the set of solutions is given by the pairs 2, 1 and 1, 2. And if you want to check to see if you didn't do any mistake in your calculations, you can go and substitute with these numbers and see if they verify the equation. If we go there, so we do 2 plus 1 will be equal to 3, so that's correct, and 2 times 1 is equal to 2, so that's correct. And because this is symmetrical, we know that this is gonna work also, but you can check it too. So 1 plus 2 is equal to 3, and 1 times 2 is equal to 2, so we know that we correctly solved this non-linear problem. Let's go to the second example. Now we're gonna solve x plus y is equal to 4 and x times y is equal to 4. And we know that x times y, which is p, is non-negative, and therefore we need to calculate s squared over 4. And when we do so, we find that it is equal to 4, which is exactly equal to p. So now we are in our second case in our chart. So the nonlinear system has only one solution in R squared, given by x naught, where x naught is given by s over 2, and therefore the set of solutions is given by 2, 2. And we can verify that by substituting these numbers in the system. And when we do so, 2 plus 2 will be equal to 4, and 2 times 2 is equal to 4. So we know that we correctly solved the system. Let's go to example number 3. We want to solve x plus y is equal to 1 and x times y is equal to 1. Now, if we go and evaluate s squared over 4, we find that it is equal to 1/4. But this time, 1/4 is strictly lower than 1, which is p. And we are now in our first case, where the nonlinear system has no solutions in R squared. So the set of solutions is empty. All right, so as you can see, like, this nonlinear system seems very trivial. Just the sum, we're looking for two numbers such that the sum of those two numbers is 1 and the product is 1, but there are no such numbers in R squared. It's very interesting. Now let's see if we just add a minus to p. You see how this fourth example is very similar to the third example. The only difference is that we're adding a minus to P. So we're looking for the two numbers such that their sum is equal to 1 and their product is equal to -1. And this minus makes a big difference, and you'll see why. Just by using the special case that we saw, if P is non-positive, then immediately we know that this nonlinear system has solutions compared to the third example where we found that this system has no solution. So right off the bat, we know that there is a difference between these two. So we know that this system has solutions. So let's go and calculate the solutions of this. And they are given by x0, y0, and y0, x0. And then we will use the same formula. S plus square root of s squared minus 4p over 2. And the result will be 1 plus square root of 5 over 2. And y0 will be equal to s minus square root of s squared minus 4p over 2. And that will be equal to 1 minus square root of 5 over 2. So the set of solutions for this problem is given by 1 plus square root of 5 over 2, 1 minus square root of 5 over 2. That is your first pair. The second pair is the symmetrical of the first one. And this will be interesting if you're not confident in your calculations. We can go and check and see if indeed the sum of these two numbers are 1 and the product is -1. So if we do the sum of these two numbers, you'll see that 1 plus square root of 5 over 2 plus 1 minus square root of 5 over 2, we put it under the same denominator, and then we get 2 over 2, and this will give us 1. So that's good. The other one is the product of these two numbers will be equal to 1 squared minus 5 over 4, and this will be minus 4 over 4, and this will give us -1. So these two numbers are really the solutions of this nonlinear system. I want to end by this final example, which has a case that we didn't check, and that is the case where P is equal to 0. So in that case, we said that immediately the set of solutions will be dependent on the value of S. In this case, S is equal to 5, and then it is non-zero. Then we know that the set of solutions has two elements, S0 and 0S. And you can quickly check if that is correct. 5 plus 0 is equal to 5, and 5 times 0 is equal to 0. Alright, hope you got something out of this video. From this lesson, you know now how to solve nonlinear systems. X plus y is equal to S and X times y is equal to P. Thank you very much for watching this MZH video. If this math episode was helpful to you, please don't forget to like the video, share it with your friends, and subscribe to our channel. The notes are available for download. Just check the description box for the link. We would also like to hear from you in the comment section. We make sure to respond to every comment. See you in the next video to continue your zero to hero journey.